Is this on? So I'm going to, so before I start on black holes, I thought I would start with some general perspective, or what Slava calls blah, blah, blah. And this was inspired by David's talk, where he started by talking about this equation. And so I'll talk about this equation too, but in a quantum and stringy context. And the question is, what is the theory of quantum gravity? How do we quantize this? And more specifically, what is string theory? What is M theory? But if we just sort of start by following our nose in quantizing this, well, we get a certain distance. So the action is familiar. And if we consider a path integral to define the theory, that actually works to a certain distance. This is what we use to calculate the cosmological perturbations of the metric when we believe the answer and go looking for them. This is what we believe to calculate Hawking radiation, which is a calculation that I'm going to do for you by the end of the lecture. And we believe the answer to a point. But of course, eventually we run into problems, and the first problem we run into is non-renormalizability. The units of Newton's constant are mass squared, and so the dimensionless coupling is or 1 over mass squared. Sorry, 1 over mass squared. And so the dimensionless coupling is e squared over mass squared. And so it grows with energy, and consequently in perturbation theory, divergences get worse at each order. Okay, we can't normalize the theory. By the way, I'm working in units where h bar equals c equals Boltzmann's constant equals 1, and then g Newton or the equivalent, the Planck mass or length, I'll keep. Okay, and this kind of problem usually points to new physics, and it's usually not easy to solve. It usually points in a fairly definite direction, as it did with the weak interaction. And even now, I think we know of a unique way to solve this problem, at least in any kind of perturbative context, which is string theory. So the action for the string worldsheet, I'll put it in the Polyakov form, just because it's a little easier to write. There's the Polyakov action. Now, I'm actually going to do very little with this. What I mean by string theory now is ADS-CFT duality, and I will develop this as we go along. But for now, I'm reviewing some physics from the previous millennium, doing some scientific archaeology. And so I want to talk about the first place, well, pretty much the first place this equation appeared in string theory. And so this describes a string moving on in a flat space-time. There's the flat space-time metric. The natural thing to do is to replace this with a general curved metric. And what happens is, there's a problem. So in the flat space metric, there's a symmetry. There's Weyl invariance. So there's this worldsheet metric, this two-dimensional metric gamma AB, and the symmetry here classically in which this gets rescaled in a position-dependent way. But when you go to quantize the string worldsheet action, there are quantum anomalies, and oops, sorry, I'm using lowercase g for this metric. There are quantum anomalies, and the condition for this not to be anomalous is Einstein's equation. That's pretty remarkable because you can phrase that result without referring to string theory at all. And in fact, that's, I think, how it first made its appearance. This is just a two-dimensional field theory, two-dimensional quantum field theory, 1 plus 1-dimensional quantum field theory. The x's are scalar fields in that theory. This is a nonlinear sigma model action. And so one is studying the Weyl anomaly, the conformal anomaly in nonlinear sigma models. And remarkably, Einstein's equation makes its appearance as the condition for that quantum field theory to be renormalizable. And then reinterpreting this quantum field theory as the world sheet of a string then puts that equation that into context. It says that the string can only propagate consistently. That this is necessary for consistency. The string can only propagate consistently in a space-time background that satisfies the field equation. Now, pardon? Actually, I'll come back to D. I'll come back to D. There's actually. Let me come back to that since you raised it. I was wondering if somebody would. But there's another thing that you might have raised here, which is I don't have any matter in the equation so far. There are other fields one can add, tensors and dilitons, which provide the matter in this equation. But I didn't bother to write them. So far this would just be 0. Okay. Good. You're both jumping ahead of me. You're both. I knew it would happen. You're all. Yes. You're both jumping ahead of me. They read my book. Yes. Yeah. You could write a whole book about this equation, but I wouldn't recommend it. Yes. There's another way to connect the string to Einstein's equation, which is the same thing, but it's a different technology, where you calculate. So first of all, you quantize and you find there are massless particles, including massless spin 2. Then you calculate their scattering amplitudes using stringy technology, and you see that the amplitudes you get correspond to this action. Now, right, as has been mentioned, of course, this equation is very revered, but high-energy theorists have very little respect for equations. They only respect symmetries and dimensional analysis. And so what actually comes out of this analysis is, indeed, just to first approximation what I wrote. But then there's order alpha prime r squared plus order alpha prime squared r cubed plus ... This is not such a magical equation. It's just an effective equation, as all of our quantum field theory equations are. And also, while we're not respecting the equation, there's another term which we could include dimensionally, order 1 over alpha prime g mu nu. Now, actually, it's interesting because in the bosonic string to leading order, the precise coefficient here is something like 26 minus d over alpha prime. So we actually choose to study this bosonic string in the dimension in which the cosmological constant vanishes to leading order, although really we still don't know of in string theory any principle that would prevent this from getting quantum corrections aside from unbroken supersymmetry. And so to the extent that we understand this within string theory, its typical magnitude in a realistic vacuum is always going to be of order the scale of SUSY breaking to the fourth. Now, I'm not sure how my lectures are going to go, but if I have time in my fourth lecture, I might say a little bit about, indirectly, about the understanding of this term within string theory, but it's not my main subject. So there is Einstein's equation now. It's kind of been uglied up by all of these corrections.
But
Now,
it always comes with plus sign, right?
Oh,
Cosmological constant.
no, well, actually, 26 minus d. So I forget which way it goes. I think actually above 26 dimensions it's plus, below 26 it's negative for the bosonic string. And it's not really a cosmological constant because it depends on the dilaton. So it's even more complicated than that. Yeah. Okay. So the question is, what's the right equation? So in string theory, the graviton is just one of an infinite tower of states, and so one natural thing to try is to embed the metric in an infinite component string field. So I went and found one of Barton Zweibach's papers so I could actually write down the string field equation. It's probably it. Well, I could have guessed, but q psi plus the sum from n equals 2 to infinity, 1 over n factorial. I'm not going to define what any of the symbols mean, but okay, equals 0. So there is some infinite component equation which contains Einstein's equation, but it's not so nice. It's not so nice. What would you like this equation to do for you? So actually, the string amplitudes, of course, are infinite series. So there's a one loop term correcting this, and a two loop term. And so on. So the minimum, at the very least, you would like this string field theory, first of all, to generate this series. But of course, even better than this, you would like this field theory to tell you what the sum is, because the series that we get in quantum field theory and in string theory don't converge. In the case of quantum field theory, we learned how to sum this up when Wilson explained the path integral in the normalization group. And in string theory, well, this would have been one way to try to sum this up. But it has problem. One most immediate problem is, in fact, it's a very compact notation, but there's a cheat here, because you have to repair these vertices at each order of perturbation theory to make them match. You actually have to work backwards, in effect, from this to this. So it's really a repackaging of what you already know without seemingly any much, especially for the closed string, value added. And so far, this hasn't been a useful way of
And it's unlike a field theory action or point-electronic equations, it probably doesn't contain non-perturbative.
Right, that's right. If it has to be corrected at each order in perturbation theory, how could it contain non-perturbative effects? In some sense, this is more like an effective theory than a fundamental theory. On the other, the miraculous thing about ADS-CFT duality is that ADS-CFT duality knows how to add up this series. It knows what the exact thing is to which this is an approximation. It's easy to forget how amazing ADS-CFT is at so many levels, but here's one of them. Actually, not most quantum field theories, well, n equals 4 super Yang-Mills and many things like it, know how to add up this series. If you ask them the right question, the answer is the sum of this series. And so, that's a fantastic fact. And it's why, in fact, that's why I say I'm not thinking of string theory this way. I'm thinking of string theory in the context of ADS-CFT. One of the themes I'll get to by the end of my lectures, though, is that ADS-CFT, wonderful though it is, maybe shouldn't be our only way to think about string theory, and maybe there should be something more directly gravitational, more directly bulk related that we haven't found yet and need to find. And I'll try to, and this is because ADS-CFT seems to be inadequate for at least some purposes. Okay, so so besides the fact that this theory is only seems like an effective theory, we also know that the strings themselves are only present in some classical limits of M theory, the complete quantum theory, and not others. So again, they're quite kind of demoted in how fundamental they are. And so the questions we want to answer eventually is what are the basic building blocks for whatever the theory is. But the things I'm talking about, black holes, even seem to be calling into question some very fundamental things we'd like to answer. What is the basic framework for the theory? Is there a Hilbert space in general? And if there is a Hilbert space, how are wave functions connected to observations? Is it in the usual way, or is it some generalization or modification of that? And again, this is in tame spaces like ADS space, this doesn't seem to arise, but it arises when you try to think about the insides of black holes and maybe about cosmology. Okay, so that's the blah blah blah. And so now I'll start talking about black holes. I haven't ever given lectures on this subject before, and so please feel free to ask questions to a point. Because I don't want to lose people by forgetting something or saying something ambiguous or going too fast. So what I'm going to do is really take you through the whole story of the information paradox, its relation to ADS-CFT, and finally firewalls and attempts to evade them. And so today, black holes and Hawking radiation, and as far as we get. So the Schwarzschild metric, let's start over here. Okay, R sub s, Schwarzschild radius is 2gm. And what I want to do is I want to, just to get started at the beginning, to talk about the geometry at the horizon, to talk about, so there's an apparent singularity here as r goes to the Schwarzschild radius. And I want to go through for several purposes. I want to sort of build up our understanding of the geometry near the horizon. And I want to start by actually going through the coordinate transformation to a smooth space. But I just want to focus on the region near the horizon. So the first thing I'm going to do is to expand near the horizon. Delta is the is r minus r sub s, and so this becomes approximately then minus delta over r sub s dt squared. Plus r sub s over delta, d delta squared, plus r sub s squared, d theta squared, plus sine squared theta, d phi squared. And to make this look more familiar, small change of coordinates, delta is rho squared over 4 r sub s, and this becomes minus rho squared over 4 r sub s squared dt squared plus d rho squared. Now, this might look really familiar already, but to make it look even more familiar, and because we'll need it for other purposes, I want to talk about the Euclidean version of this metric. Parentheses somewhere? Sorry. Oh, where? Sorry. Oh, it's this times that. There's no parenthesis. I mean. Oh, that. Sorry. Oh. Yeah. No? My I don't. I mean, this multiplies that only. Is it ambiguous? Okay. Okay. So let me also, in parallel, do the Euclidean version of this, where we just flip the sign of the first term. So it's now rho squared over 4r sub s. Actually, is there? That's squared. Yeah, 4r sub s squared. D t sub e squared plus d rho squared. So now we see, of course, this is just the metric of. I'm not carrying around the two-sphere, which is just doing the same thing everywhere. We see that this is just the flat two dimensions in polar coordinates. So defining x equals rho cosine tau sub e, t sub e over 2r sub s, and y is rho sine t sub e over 2r sub s. This just becomes dx squared plus dy squared. Okay, so for the Euclidean version of the metric, we've gotten the coordinates in which we see it's locally flat. Here we do the same thing except with coshes. X equals rho cosh t over 2r sub s. Y equals rho sinh t over 2r sub s. And this becomes minus dt squared plus dx squared. Okay, so indeed we've shown, well, we've gotten rid of the singularity, and I guess I should draw a picture somewhere. So, well, I'll keep moving along. So this is the tx plane, and the part that we started with, the part that is covered by the coordinates t and r, you see here is where x is greater than the magnitude of y, which is x is greater than the magnitude of t. Excuse me. That's t, which is region 1. So we've found that the metric is smooth there, but we've also found that the space can be extended to 3 additional regions. This is the part that we can see, and this is the part that we can't see, but we can theorize about.
Sure.
Yes.
Can I ask a question? You see, because when you introduce delta is equal rho squared, you prohibited negative delta. So it means that you don't allow yourself to go inside horizon.
Sorry.
Because
Yes.
inside horizon there will be change of sign.
Right. No. Sorry. So the good. So the coordinates. Good. The coordinates r, t, delta, rho don't cover the whole space. When we finally, it's only when we got to x and t that we got the coordinates to cover the whole. That we cover the whole space.
No,
Right.
no, but at the beginning of the, you made this kind of thing because you know
Yeah.
in the Euclidean version
Yeah.
you are not allowed to go inside horizon.
Right. Right. So yeah.
That's the reason
Yeah.
you never
So in the Euclidean, so yeah, just to, I mean, in the Euclidean version is just the continuation of region 1. That's right. That is the Euclidean version, interestingly, knows only about region 1. The Minkowski version knows about all 4.
What should I do in these coordinates when I want to penetrate through the horizon?
The Euclidean ones?
No, even in Lorentz, because you took delta is equal rho squared.
Well,
I have to consider rho to be complex if I want to go in region 2.
No, I don't want. No, I'm the first. Maybe I did this. Maybe I went through more coordinate changes than I needed. But the up to a point, I was only using coordinates that are valid here. And at some, finally I got to. I did it in an extra step. Maybe I shouldn't have bothered. But finally, I got the coordinates x and t that cover the whole plane. So, I mean, the answer is you don't. Rho is not a. RT, rho, delta are not good coordinates outside of region 1. That's all. Yeah, yeah. Okay. Also, to extend this to the whole geometry, it's useful to go to light cone coordinates, v is t plus x, u is t minus x, and so this metric becomes minus du dv. Again, I think for anyone who's studied relativity, this is all very old stuff, but I want to start slow. Okay, so this was only looking near the singularity. There is, of course, we can extend this to the full geometry, and I want to draw the full geometry, and I'll also write the coordinates to cover it. So coming back to the full coordinates, the full metric, and I'll use this a little bit. Okay. Okay, so this is the same. So I could have just done the entire space at once, but I thought it was easier and less writing to just do the neighborhood of the would-be singularity. But in terms of these coordinates, the full metric looks like this. You have u equals 0. You have v equals 0, and then you have your regions 1, 2, 3, and 4, and then the original r equals r sub s. You see, there's nothing. Everything is smooth there. This is smooth there. Everything is smooth at r equals r sub s. R goes to 0 is still a singularity. In these coordinates, r equals 0 is uv equals 1. And so uv equals 1 can either be up here where u and v are both positive, or down here where u and v are both negative. Now, I'm only going to, various lecturers, including Mark already, will be talking about the two-sided geometry. I'm only going to be talking about black holes that form in collapse. So that means that there was some infalling body that followed a path more or less like that, and only the right side, I should be using colors here, only the right side of this infalling body is relevant, and on the left side one fills that in with a smooth space. Also, as you look at later and later times, older and older black holes, so you're moving up here and you want to use the boost symmetry to pull that back down to here, the infalling body will sort of more and more closely follow this v equals 0 line. And so you get sort of for an old black hole, just you have most of region 1 and most of region 2. Yes?
Should we say, so you say this is the full geometry. I mean, I guess maybe we could say that this is a full geometry that has that region 1. And we always write this geometry down.
Yes.
It's very symmetrical. But
Yes.
I mean, is that biasing our...
Well, in fact, I'm not writing it down. You're writing it down because I'm just writing down the class geometry. So what I'm writing down is the geometry that you actually get, starting from vacuum and throwing in something.
Even with, you've got a bit of region 2. So
I got a bit of region 2. Good.
we're making some assumptions here.
Well, so okay, good. So suppose let me. I'm going to have to redraw this anyway. So let me. You're talking about even for the infall, we're making assumptions. So let me erase the part that doesn't matter, and glue in the part that doesn't matter for the collapse geometry, and glue in just an ordinary origin. So we have this, and now you're questioning even in this case, are you, whether this is meaningful?
Well, I guess I'm saying that maximal geometry you wrote down is I guess a choice. You could have other stuff happen behind the horizon, and then you took a
Ah, right, right.
Was that something?
So I think, I mean, so I'm not a relativist. I'm not a relativist, but I think general relativity has a Cauchy problem. Cauchy, yeah, there's a well-defined Cauchy problem, which means if I give you the geometry here, there's a unique evolution forward, and this is it. If there's a relativist here, please speak now or forever hold your peace. So no, I mean for this, so for the collapse geometry, I don't think there's any issue. I think
It's the only relevant geometry for physical situations. The rest is garbage.
somebody might throw you into a black hole someday, and you may rethink this. Here, you say I have to assume something here.
About the state inside the actual, what is the collapsing body?
Well, okay. I mean, right. I haven't. Of course, this could be made of different things, which will change the geometry slightly. But for each given type of matter, there's a Cauchy problem, a well-defined, a well-posed Cauchy problem. Yeah. No, I'd like to talk about the two-sided case, but the one-sided case is confusing enough. So I'll let Mark talk about the two-sided case. Okay, so now, with that warm-up, let's come back to the Euclidean metric. And in the Euclidean metric, the Euclidean time is a periodic variable. It's periodic with period 4 pi r sub s. Which is a sign of thermal behavior. If we look at this full geometry, if we look at, let's see, actually, that's amusing. I hadn't thought about that. If we look at the full, if we look at the Euclidean version of this geometry, yes, which is just the Euclidean version of region 1. It looks like that, where the would-be coordinate singularity, where the t direction, the metric of the t direction goes to 0, is smooth. That's down here. But also, as you go out asymptotically, the metric goes to 1 in the t direction, and so it just becomes a circle with that circumference. And of course, we know that a Euclidean circle generates a path. That path integral on a Euclidean circle generates a thermal partition function. So if you do the partition, if you calculate the partition function, the path integral for quantum fields on this geometry, what it describes is a gas of quanta in equilibrium with the black hole. And it's in equilibrium because, again, this is a Euclidean geometry. There's no time dependence. And so already from the fact that the geometry is Euclidean, that the Euclidean geometry is of this form, it seems that we learn that the black hole has a temperature. Also, if the black hole can exist in equilibrium with the gas of quanta, then since of course it can absorb them, it must be that it can also emit them. And it's remarkable that one can come to that conclusion just from this little bit of analytic continuation, but in fact, that's the right answer, as we'll see in other ways. Now, if we have a temperature, we also have an entropy. ds is dm over t sub h. And if you plug in the relation between t sub h and the radius, and then in terms of the mass, and integrate, you get the Bekenstein-Hawking entropy, pi r sub s squared over g, which is the area of the black hole horizon over 4g, the Bekenstein-Hawking entropy. Now, before I go on, there's a question, what is the entropy counting? And we now think we know it's counting excitations on D-branes or something. But there's an interesting answer to this question already given by Jacob many years ago. And it's worth recalling that. And I'm going to need my black hole again. But if I get this wrong, please correct me, Jacob. But the basic question is: suppose that we have our black hole, and we're still classical now. We're not concerned yet with Hawking radiation. We have our black hole, and we gradually build it up by throwing quanta in. Now, for a quantum to fit inside the black hole, its size has to be no larger than the Schwarzschild radius. So for each bit, the increase in the energy of the black hole is 1 over the Schwarzschild radius. So actually, let me do this in the right order. And so the change in the number of bits that we've thrown in is the change in the mass divided by delta E. So it's the change in the mass times R sub s. And if we integrate this, this is like dr sub s over g r sub s, which is again like d of r sub s squared over g. So by counting the number of bits that one could throw into a black hole of a given mass, one gets to the same number, same order of magnitude, and interpreting each bit as carrying 1 unit of entropy, you can either throw it in or not throw it in, or maybe throw it in different states of order 1 unit of entropy. You could conclude from that argument that again a black hole of a given mass or size can carry a definite number of bits of information. And is that close enough? And that gives a picture of what these microstates are, which is, I don't know if it's, well, it's worth drawing because we don't draw it very often, but it's the first picture we had of these microstates. Here's our black hole again. And now let's take a space-like slice that does this. So outside it's just some kind of roughly constant time slice, but as it passes through the horizon, we keep it away from the singularity. It's following some hyperbola here, but it stays away from singularity. All of these bits that Jacob threw in are still on that slice. And so the microstates, from this point of view, are just the possible states of the ingoing matter on a space-like slice like this. Also, recall I told you that as the black hole gets older, there was the infalling matter. As the black hole gets older, this is going more and more to the left. This slice is getting longer and longer. So as we throw in more stuff to make the black hole bigger, this slice is getting longer and longer. There's more room for these states, and so that's how the entropy is going up. There's things I don't understand about this, and if you have questions, you should ask Jacob, not me. But this is one way to think about the microstates. Questions for Jacob?
It's not the microstate, it's the microstate that's created the black hole. It's not the microstate of the black hole itself.
Well, I mean, it's what the black hole is after you made it. I mean, that's seemingly where the information that you threw in resides. Yes. Not sure. Well, there are problems with, of course, as we'll come to, there are problems with this picture, but well.
If it would exist forever, then the amount would be infinite. Because
Oh yeah. Once it yeah.
If you would assume
Yeah.
lifetime is MQ,
Yeah. Well, once it starts radiating, then the story changes. And yeah.
but you know that in this sense, future of the black hole define you the maximum volume inside the horizon, which you can encompass.
Yes.
you would have infinite number of configurations because, as you understand, if you will take quanta
Mhm.
and change its location, then
Yeah.
you
Yeah. There's a question. Yeah. Actually, I think if I understand what you're saying, there's actually more. I think this overcounts the states because there's locational information. I think is that what you're saying? There's locational information as well.
it's
Yeah. I
location
actually
information, so
I don't want to go down this too far because, but there's other. But I do have. That's exactly. I think this seems like there's more states than one might have
no,
thought.
but if you take into account the black hole finally will disappear,
Well, then there's.
you will get perfect
Oh,
account.
what we'll talk. The problems that we come to when the black hole evaporates, we'll come to. Yeah. There was another question.
So why are you saying it doesn't reach the singularity? You choose it?
Oh no, I'm just choosing it the way. I'm choosing to look at a slice that avoids a singularity. Right. If I this once I could.
More than one bit of information occurs needed to be built up a black hole.
She spread the newspaper on the table in front of them and pointed at 10.
So here's our horizon again, and we have some infalling person. Imagine that they're sending out pulses rapidly, regularly and rapidly as they approach the horizon. Well, it only takes a finite amount of proper time for them to cross the horizon, so they'll only send out a finite number of pulses, which means for the observer at infinity, these pulses are arriving more and more slowly as we these pulses are rising more and more slowly. There's a very nonlinear relation between the time a given mode passes in this geometry, in this region, and the time it reaches infinity. In terms of the proper time here and the asymptotic time t, delta t grows exponentially with delta tau. And again, that's follows from our discussion of the. Actually, I think I might have forgotten to write all of this. but it follows, if you go back to the coordinates capital U and capital V, which are the good coordinates here, at one point there was a relation between U and V and an exponential in time, and so hidden in those coordinate transformations were this fact, that there's this exponential relation between these time steps. So what that means is, as we emit a mode, as it moves away from us, it's being redshifted. Or equivalently, if we consider a mode out here with a given frequency and follow it back, the further back we follow it, its frequency is becoming exponentially blue shifted. So I'm going to use the terms occasionally redshift and blue shift, which again just refers to the fact that these modes here are getting lower in frequency as we move forward in time. We follow back where they came from. Their frequencies were much higher, as would have been seen by an infalling observer who is passing through them. So the nonlinear relation between the times implies that when we go to frequency space, the frequencies seen by the outside observer and the infalling observer are all mixed up. In particular, positive and negative frequencies get mixed up with each other, and so the two observers, if one interprets the state as empty, the other interprets it as having particles, and vice versa. But also the fact that these modes, if we're talking about a mode of order 1 frequency out here, having very high frequency over here, the adiabatic principle implies that the modes are empty in this region of space-time, and therefore, by what I just said, they are partly populated once they're seen by the asymptotic observer. So that's where Hawking radiation comes from, and so I'll go through that.
Can I ask you some questions?
Yes?
You say that Hawking radiation comes from the radiation which is emitted by some...
No, I didn't say was it. No, I did not say that.
But what does it mean?
The emission was, I was just doing the emission to, so let me not mix up the emission there was just to explain this nonlinear relation of the times.
So this line when you say
Now forget the observer. The observer was just there for the purpose of deriving this. Sorry. Yeah. So now there's no observer, there's empty space, there's no radiation here, there's radiation there. Good. Let's see. I guess I don't have my metric anymore, but that's okay. Yeah. Oh, I do have. Okay, good. So thank you. So I'm going to do a toy calculation, in which I just consider a massless scalar field in 1 + 1 dimensions. So I'm just going to keep the 1 + 1 dimensional part of the metric. And in these coordinates, the Klein-Gordon equation is just partial u partial v phi is 0. Okay, now I actually do need so these are the coordinates again, which are smooth across the horizon. I also need the coordinates which the asymptotic observer would use.
So now you're not considering any more collapsing modes?
Good. That's a good question, which I'll answer as soon as I write these, because I'm going to come back to this. But I'm using the, where's my horizon? There. Okay. So I'm using the fact that after the black hole has formed, the adiabatic principle tells me that the modes of interest are empty here. So there is a collapsing body back here, but my calculation starts later. This is not how this was originally done, but it's the right way to do it. I'll explain. Good.
But
So,
then black hole will change parameters, and how you will incorporate this change in the metric?
that is slow. I mean, because of evaporation. that's slow on the time scale of what's happening here.
Right, but normally, for instance, people are using this Y geometry, which is 1 minus 2m, which depends on V over R, dv squared plus dv dr.
The change in the metric during the time of relevance is parametrically small here. I mean, it's not
if you
useful.
consider small time interval.
The time between the time the mode is near the horizon and the time it is several Schwarzschild radii away is a tiny fraction of the life of the black hole. Right, right. Sorry, let me just. Guess I forgot to write this, but so the coordinates u and v are the ones that the asymptotic observer wants to use. They're the ones. So the modes of definite frequency in u and v are the modes of definite little u frequency are the modes that the asymptotic observer would use. The modes of definite big U frequency are the modes that the observer passing the horizon, or well, we don't have an observer. They're the modes that describe the geometry smoothly in the neighborhood of the horizon. And again, they're related exponentially, or I've turned it around so they're related logarithmically. And so, and also, of course, in both sets of coordinates, because this is a conformal transformation, it doesn't mix U and V. The Klein-Gordon equation is just that, which means that the general solution is a function of U, either U, big or small, plus a function of V. The function of U is moving to the right. The function of V is moving to the left. The nice thing about this toy model is that right and left don't mix, and so we'll only keep the right movers, the ones that are functions of phi right of big U or little u. And so there's a mode expansion, two mode expansions.
Right, left here means incoming outgoing.
Right means moving to the right, yeah, which is generally outward. Some of them don't make it out because they're behind the horizon, but they're trying their best. Yes, yes. So this is just a standard mode equation for a massless scalar field. But again, there's two of them. So capital U, these are the good coordinates near the horizon. And so nu here, not to be confused with V, nu here is the frequency that would be measured in this frame. And now the same mode expansion, okay, I'll call omega the frequency seen at infinity. And so A's are the modes near the horizon, and B's are the modes that are natural to use at infinity. Okay, I hope that's all readable. Okay, and so two mode expansions. And the adiabatic principle says that the modes that are good near the horizon, the modes that are good, we use here, are empty. A sub nu, to very good approximation. Exponential. The adiabatic principle is good usually to exponential corrections. These modes are empty. So this is the statement that there's no that if you pass through if you were to pass through this region, you couldn't find any modes of high energy because the adiabatic principle says there's no way they can form, given that the geometry is slowly varying on that scale. Okay, but now we write this in terms of the B modes, and we find, of course, that they're partly full. You can take the Fourier transform of here to pull out B sub omega, and then over here that gives you some kind of integral to do folding one mode into another. So that you get that the B modes are an admixture of the B lowering operators are an admixture of the A lowering and raising operators. I'll write one of those coefficients. I'll need, I guess, the one I called beta, the one that mixes the lowering and the raising, beta omega nu 2r sub s omega over nu to the 1/2. This part's imaginary and will drop out. Gamma function minus 2I r sub s omega. Okay, so just again the coordinates that are good near the horizon, the coordinates that are good at infinity, the relation between them, and consequently just by Fourier transform the relation between the modes. And so now if we evaluate in this state the number operator for these B's, okay, we write that in terms of the A's, and so we get the A dagger term and the A term, and that using the commutation relation just gives us a delta of nu minus nu prime. We end up with some kind of convolution of beta squared, and in the end, just insert, calculate, in the end you get a thermal distribution.
What happened with alpha?
Okay, good. So let me maybe insert some more. Thank you. Yeah, I want more questions from students, please. Thank you. So what we have is this becomes alpha A dagger plus beta A. This becomes alpha star, beta star. This becomes alpha A plus beta A dagger. The definition of psi is that A kills it, or on the left, it kills A dagger kills it. So the only term that survives is that one and that one. Moving the A through to psi, moving the A wants to kill psi, moving it through to pick up a commutator, and so this becomes beta star times beta integrated. And you do the integral, it actually all collapses to delta functions, and you end up with that.
So you take a principle of the vacuum state.
Yes.
The point of view of this coordinate capital and capital as nothing.
Yes, yes,
On the horizon.
yes. Now, yes.
The alphas give you something that's delta of omega plus omega prime.
Pardon?
The alphas do give you something, but it's delta of omega plus omega prime.
Right, yeah.
And then that, because omega, both omegas are positive,
Right. So here's our thermal distribution, which we had expected. Now, so there's a point about the calculation which, so Hawking's original calculation, as has already been alluded to, was rather different, because he followed the modes back all the way through the infalling star and back out again, and then he assumed they were empty here. And that might seem more legitimate to you because it's a real calculation. You don't have to wave your hands about the adiabatic principle. But this calculation is completely dishonest because, first of all, he assumes the star is transparent. What if it's not? But even worse, this mode that we're following back is more and more blue shifted. So by the time it passes through the star, the energy of it is enormous. And if you used a real star, it would not pass through it. You couldn't even follow dynamics because it would involve physics that you didn't know. And the point is, you don't need that. You don't need that. He knew what he was doing, of course, Because the point is, the adiabatic principle, as I described, gives you the answer uniquely. All you need is any model that respects the adiabatic principle. And a transparent star respects the adiabatic principle, even if it's not physical, and you will get the right answer. I haven't really studied the literature. Maybe somebody knows better than me.
But why you say that it's dishonest calculation? Besides of transparency, you have exact solution for collapse shell.
Right. But you
In principle, of course, then you can take as initial state in this case, initial Minkowski vacuum.
it's true.
Principle.
You can decree you have a form of shell through which trans-Planckian particles. No, but actually, I think there'd be a gravitational interaction between that you couldn't ignore. I think there is
no so-called back reaction. You see of this kind of emitted water, but otherwise, okay, solution for the dust shell is perfectly good solution. I have nothing against your derivation. Moreover, actually, I have the same derivation precisely in the book which I wrote.
Okay. So good. That's a reference. So.
Calculation in this sense is also completely honest, as I would say.
Well, maybe.
Sure, just mix irrelevant thing with the relevant thing, but you pick up relevant.
I think there's I think you're making an assumption of very high energy physics in there that I should. His calculation. His calculation certainly has made some people believe that the answer depends on physics above the Planck scale, which it doesn't.
No, it's actually, you see, it's formally loops. It's the same story as
Yes.
trans-Planck frequencies in cosmological.
It's the exact same story. It's the exact same story, right?
We were discussing
Right.
this problem
Right.
already. But
Right.
it's in fact actually some kind of fictitious problem related with convenience of calculation.
Well, one is assuming that the ultraviolet physics respects the adiabatic principle, which, as Lindy points out, if it were not true, we would immediately fry because the expanding universe would be making particles from the redshifting of modes. Yeah.
We do not know even.
Yes.
Okay, we approximate our equation to
Yes.
the region where we have no idea what to do, but you can do step by step changing coordinate system on the way. You see,
Mhm.
if you don't want actually to get inside these super Planckian scales. By the way, it's
Okay.
different thing, but
Okay. We can come back. Yes. No, Rami.
That must be actually related to the validity of the
Yeah.
adiabatic function.
In the equations, do you have equations that are different from Polchinski's 76 paper?
The answer is the same, and equations that are different. Well, again, the framework is different because I have equations. He has equations I don't have that describe the evolution in this period. That's all. Right. I'm just. I think we all agree on the physics, but I want to use the words adiabatic principle because it really is it's really the reason the calculations give the right answer in cosmology as well. Yes. The adiabatic principle? So, I mean, the adiabatic principle says that if you have a Hamiltonian which is a function of time, and in this case, so that's good. So I was going to do this later on, but since you've asked, the adiabatic principle says that if you have a Hamiltonian which is a function of time, then provided the changes in the matrix elements are small compared to the distance between levels, you will basically not undergo a transition. And in this case, the change in the matrix elements is governed by the rate of change of the geometry, the curvature scale of the geometry. The difference of levels, again, is this very high energy because of the blue shifting. And so if you really wanted to as far as I know, the adiabatic principle is best derived or used in a Hamiltonian framework. What you would want to do again is you would want to foliate the geometry in some nice way. And these slices doesn't matter what they do way inside because you would want to foliate the geometry in some nice way and do a Hamiltonian calculation in those time slices. In those time slices, the adiabatic principle, as I described it, would apply. So that's kind of that's what I have in the back of my mind when I say the adiabatic principle tells you that these modes are empty. Thank you. Yeah. Okay, so I want to make two more comments about the Hawking radiation before I go and start on the information problem. The first is that the main difference between this simplified model and the full geometry is that in general the ingoing and outgoing solutions aren't independent. One can, in fact, frame this kind of as a barrier penetration problem where there is some amplitude for the outgoing mode to get out and some amplitude for it to reflect. And in that case, you would have a transmission coefficient here. Then you would have a reflection coefficient and the mixing with the ingoing modes. And up here, you would have the transmission factor squared, and this is known as the gray body factor. The gray body factor grows rapidly with angular momentum. So once we go back to the four-dimensional problem, we have angular momentum, incoming modes. Well, you would expect, of course, with a large angular momentum, there'd be a large impact parameter. It would be harder to get to the horizon. And in fact, the gray body factor, the transmission amplitude falls exponentially in the angular momentum.
When you got gray body factor, what was your explanation?
Nice.
Your problem when you reduce to two-dimensional scalar field, which by the way is conformally invariant.
Right.
There is no gray body factor.
Right. So what I said,
Make reduction.
when you lift back to, well, when you lift back to the full four-dimensional thing, or when you take the two-dimensional model is not the same thing that you get if you start with the four-dimensional problem and expand in modes. There you get an additional potential effectively in the wave equation.
You will make
Right.
reduction to two-dimensional case,
Right.
four-dimensional
Right.
problem. Then
Right.
you are getting extra external barrier.
That's right, external barrier, and which has the effect that, so you have your I guess A here, B here, and C here, and so B is, when the reflection is large, B is mostly C. But and it's so there's
No, but if you focus
Yes.
even about involved,
but I mean that
there will be just equation actually for the scalar field will be changed by extra potential. Linear equation.
right, and this is what right. The equation has extra potential, and then as a consequence, the final relation between the modes near the horizon and the modes in infinity is both scaled downwards, but by unitarity,
Which
there's
is raised by the way entirely classically, therefore
Yeah.
it's completely irrelevant. I mean,
Yeah.
besides of penetration, I mean, it has nothing to do with Hawking radiation, because this is penetration of this completely thermal radiation when it goes through the barrier. I mean, gray factor appears from there, therefore
right. Yeah. Well.
my shield to the entropy.
Right. I mean, just to coming back to thermal. I mean, I'm not sure if this is what you're saying, but coming back to thermal equilibrium, you know that we know if a body reflects more, it must also then emit less in order that it can exist in equilibrium. If I put it in a gas, if it reflects stuff, then it won't absorb as much, and therefore, to stay in equilibrium, it has to emit less as well.
Right.
So I think what you're saying is that basically this is a purely, we can think of this reflection as a purely classical effect. This is the albedo of the black hole, and the larger the albedo, thermal equilibrium requires the smaller the emission. So this follows just from thermal equilibrium. Question, student?
How are we sure that that temperature that rate is a property of the black hole and not of the scalar field?
Well, the first answer is it was the same temperature that we deduced from the geometry, and it. So I'm not sure what you. Well.
Here's the surface curvature of the
Mhm. Yeah, I mean, I guess I'm not sure how you, in what sense, it's a property. I mean, the black hole radiates at this temperature, and it does so for any kind of. I mean, the temperature is independent of the kind of field that you look at. Independent of the mass of the field, its spin. The gray body factor depends on the mass and the spin, but the once you peel off again this reflection, then it's the same thermal factor for every field.
+1
With a +1 for fermions, yes. Yes?
Can you comment on the Euclidean version of this computation similar to the Schrödinger production? Do you get exactly the same?
Wait, say again, sorry?
The Euclidean version of the computation, like in the line of the Schrödinger production.
Yeah.
Is it really identical?
You mean? Okay, so this, the. Are you referring to the Wilczek Parikh paper?
Yes, which I never understood.
I've never understood it either, and I'm.
Let's continue.
Let's continue. Yeah. Okay, so again, I wanted to mention the gray body factors because one has to think about them now and then. And the other thing I want to mention, I want to also introduce another set of modes because, again, the capitalized coordinates are the ones that cover the whole geometry and go inside. The small u coordinates are the ones that stay outside. And so they're the ones which are basically built out of the Schwarzschild R and T. And so I want to also basically complete the B modes with a set behind the horizon. So the B's live out here, the A's live everywhere, and so I want to introduce some modes B hat on the inside. And now, when you write, so I wrote again, leaving out the integrals and the factors. I wrote that B is a sum of A's and A daggers. When we turn that around, A is a sum of B's and B daggers, and B hats and B hat daggers. Again, with integrals and coefficients. And it has to be because, as you see, we need A covers the whole region, B hat and B cover the parts. And now the A vacuum, the state which is annihilated by the lowering operators for A, I want to write it in terms of the B's and B hats. And I can do this immediately. There's a normalization constant, and then E to the minus the one coefficient I can't. Here we are. Okay, so this is just another way to state the relation between the A and the B mode operators, stating it in terms. So this is again the state annihilated by the A lowering operators. This is the state annihilated by the B and B hat lowering operators. This is a Bogolyubov transformation, or a squeezed state. And so how do I write this down? So first off, this kind of relation always gives you this exponential of product of raising operators. But secondly, there's a symmetry. The black hole has a time translation symmetry. That symmetry is broken by the collapse. But again, because of the adiabatic principle, the collapse doesn't affect this calculation. It also is modified by the slow decay of the black hole, but that's small on the scale that we're looking at. So there's a time translation symmetry here, and this expression has to respect that time translation symmetry. So this is the asymptotic time translation symmetry, which is conjugate to the total energy of the black hole, to its mass. And the B's are raising operators for that mass. Now, the following had better be true, though, that the B hat daggers, the things that you want to call raising operators because they are locally interpreted as creating energy, creating particles, have the opposite sign in this commutator. And this has to be true because, well, first off, this is necessary in order for this state to be translationally invariant. This has to commute with the Hamiltonian, so the signs are opposite. If we had a positive sign here, we couldn't write anything here at all because we'd have positive with B's and with B daggers and sorry, there'd be nothing we could write here at all. So in order to write a non-trivial state, this sign had better be here. And if I had actually gone through the effort of writing out the mode expansion, you would have seen it appear. Now, it seems odd that a raising operator should lower in energy. But the point is that we're talking about the Hamiltonian, which is the symmetry associated with a killing vector, which does that on the outside. It's time-like. And it does this on the inside. It's space-like. And so this index omega on these inside modes is actually a momentum. It's not an energy. And so it can have either sign. And again, when you do go through it, you find that these raising operators lower the energy. And again, they must do that in order to be able to write down a non-trivial state. And then the only thing that's left is the normalization factor, which you get from by comparing with the result for the number operator. Occasionally when you're reading about Hawking radiation, you'll read that the inside Hawking modes have negative energy, and that's what this means. And this comes up now and then, so I wanted to mention it.
Forgive me. Can you remind me of the motivation for applying the B annihilation creation operators A's vacuum state rather than the A annihilation creation operator, the number operator on A's vacuum state? Why?
Good. So what? I mean, let me ask if this is what you. So this is a state of the black hole, and the physical information we have about it is the adiabatic principle. It's A empty.
That's vacuum state for A.
Yeah. So right. So a black hole state that forms and collapses, if we don't do anything spectacular to it, will be in the A vacuum. The B's here are the mode operators as seen by the observer at infinity. In the mode expansion, they were the ones expanded in terms of the omega here is the frequency with respect to the external time. So these are the mode operators that the external observer would interpret as creating and destroying particles. And so what this matrix element asks is, what is the number of particles seen on the outside in a typical black hole state? Yeah, more questions from students, because I don't want to go too fast here or get too distracted by, subtleties that people bring up. So I have a little bit more time, and I'm going to. So what I'll do is I'll lead into my next subject, but I want to pause and just ask: are there any ideas or why I did things that are not clear? Good. So. Let's suppose we have a harmonic oscillator with a time-dependent frequency. So minus del squared over 2m plus m omega squared of t. There's our Hamiltonian. And now suppose that the frequency, we started at a constant value, we wiggle it for a bit, and then we take it back to another constant value. And suppose the oscillator started in its ground state. The question is, what is the probability that it ends up in its ground state? And this is all a linear problem, so you could turn to linear equations. The statement is that as long as omega dot, the rate of change of the frequency, so over omega squared. So this is dimensionless, omega dot over omega squared. When this is small, then the probability of ending up in anything but the ground state is also very small. So the probability of the ground state going to anything else is exponentially small. And if you want to know where to learn about this, the answer is probably Landau and Lifshitz, right? Yeah, this is something which is really important, and it's hard to find, I think, a really nice treatment of it in the textbooks. But it's one of those very basic physical, principles that should be really, emphasized in quantum courses. Yeah. Yeah. It's surprisingly difficult to show. I mean, it is surprisingly. So in the case at hand again, this is we're doing free field theory. So it really is just a harmonic oscillator with a time-dependent frequency, and the rate of change of the frequency due to the geometry being curved is small compared to the very highly blue-shifted frequencies that these modes have in the region that we're looking at them. Yeah. Question.
When you justified that this is the existence of Hawking radiation, so you looked at the number operator for a certain frequency, and you got the right result.
Yes.
A thermal state has other properties. So can you do the same calculation like?
Well, good.
Correlation between
Well,
operators?
so to be honest, this is not really a thermal. It's actually not really a thermal state, partly because of the gray body factors. That is, the modes are not in the four-dimensional problem. Unless these are actually not fully populated to their thermal extent, and so now if you put suppose we put the system in a box so that the Hawking particles can reach the boundary and reflect back, and the thing can come to equilibrium. Then I will assert that all properties are thermal. And the reason I'll assert that is because the way you would do the calculation then is it's a time-independent situation. After a while, you go to the Euclidean geometry, and now it's by construction this generates for you a thermal partition function. I mean, it's almost a triviality to say if we put the black hole in the box and wait for a long time, it will behave thermally. But in the decay itself, it's not perfectly thermal because it's a non-equilibrium process. But it's, yeah. Okay, yes?
The way you were describing the use of adiabatic principles here, it sounds like you're treating different modes independently, but shouldn't you be worried about the mixing of different modes in the process of the gravitational collapse?
Well, okay, the process of gravitational collapse was far in the past. I'm starting this much later. Now, I mean, of course, there are interactions. So there are corrections to this. Yeah, there are, but the scale of the corrections is, assuming for simplicity the gravitational interaction is the only thing we have, gravity is weak on long distance. So the scale of corrections is the Planck length divided by the Schwarzschild radius to some power. Yeah. Okay, so yes.
Did you check? Okay, sorry for
Yeah.
the question. Because first of all, you can remove thermal radiation. It's okay. Everything will be just a minute. But you see, of course, natural question would be also why you could not take as a state in your consideration state without radiation at infinity.
Meaning state without radiation coming in?
I mean, instead of psi, no singular state with respect to these A operators, you could take state with respect ground state with respect to B operators.
No, so you're considering state where you impose that no radiation. You impose that no radiation is coming out.
Yes.
Ah, if you impose that no radiation is coming out, then the A modes were not in their ground state. They have very high energy, and so you have a very large any-dimension tensor near the horizon. Yeah, yeah, right. You knew the answer. Why did you ask? Yes.
I asked for the benefit of students.
Okay.
Not
You're
just
very
for
good.
you, yeah, because you understand this,
Yes.
this is natural question
Right.
which arises this kind of derivation. What is wrong?
Right.
about
Well,
this?
in some sense, that's where the firewall comes from, because
Yes,
you can
precisely.
effectively project, because effectively you can project onto definite states of the radiation, and once you project onto a definite state of the radiation, I mean, right? So basically, yeah, that's right. Yes.
How much did you use of the inside matrix in your construction?
Ah, so this is kind of getting ahead, because I use the fact that geometry is smooth at the horizon.
Just
But
near or all the way through?
Well, but suppose that somebody found a way to set off bomb. Suppose right down here somebody simulated a vacuum decay, so that the entire interior disappeared. That's behind the horizon. It can't affect anything seen at infinity. So even though we use the interior as a crutch to get this answer, it can't depend on what's happening behind the horizon. It cannot. And I'll say that in another way 2 lectures from now. But in fact, it doesn't, although we use that as a crutch, it's clear on basis of causality that we didn't need it.
But even your squeeze state doesn't depend?
Well, the squeeze states do. The squeeze states do. But what's seen at infinity can't depend on what's
But it does depend on the existence of the horizon.
It depends on the existence of the horizon and the outside. It doesn't depend on
Well,
It doesn't depend on anything happening in region 2.
so if you took something like those fuzzball states, which have no inside, but look up to very some compactification distance, like
Yeah, with the fuzzballs, it's not. Well, yeah. Let's save that. I don't know what to say about fuzzballs. Yeah.
I think in Hawking's calculation, you see the advantage there is that you see that nothing comes out from inside the horizon, because you always look at stuff that is emitted before that shell enters the horizon.
Well.
Somehow you're replacing the inside with the adiabatic assumption.
Maybe.
I think what you
So, yeah. Maybe, I'm not sure whether I guess he's. I guess you say his calculation is more explicitly independent of what's behind the horizon.
Yes.
A good point. Okay, I need to do better then. But the claim is I can use the adiabatic principle with this hand and the causality with this hand, and with this hand LE exists at 5 minutes. So let me just set the stage for the next subject. So let's now that we know the black hole evaporates, let's again think about the experiment we talked about throwing bits in one after the other. But let's do it at a rate that exactly offsets the Hawking radiation, so that the black hole never gets any larger. It never gets any larger, but it gets older. And this nice slice that I was drawing gets longer and longer and longer, as it has to, because all of these bits that we threw in, are still inside. they can't travel faster than the speed of light, so once they're inside, they can't get out. They can't influence the state of the Hawking radiation on the outside because they're at a space-like distance. And so, yes, there's radiation going on carrying energy away, but these quanta are not carried away, and their state is not in any way carried away. And so it seems that what happens is that one can actually, in this way, produce a black hole that has a finite mass, but an arbitrarily large number of possible internal states. And even without looking in, you don't really have to look way deep inside to make this argument. You just have to say, I've thrown in all these degrees of freedom, each of which could be up or down, so each one carries a bit. Once they're behind the horizon, they can't influence what comes out. And so regardless of what's happening way deep inside, you conclude that you can prepare a black hole in a number of configurations which is arbitrarily large, whereas the Bekenstein-Hawking entropy for this thing is some finite number. And so you seem to conclude from this that we can no longer interpret this entropy as a count of the microstates of the black hole. Now, that's not so bad. I mean, easy come easy. That's not a crisis. Maybe the Bekenstein-Hawking entropy is not actually does not have a statistical interpretation. But in fact, it's a sign of worse things to come. Because well, worse things are going to happen. So what I need to talk about next is well, actually, good. There's another simple thought experiment that we can do, which is again we just take our black hole and we throw a book inside, or some quanta in a definite state, and the book or the quanta are definitely behind the horizon. And then the black hole evaporates. And in the end, we just have Hawking radiation. And the Hawking radiation cannot depend on the state that we throw in or the state of the book, because again, once it's behind the horizon, it can't, by causality, affect anything seen on the outside later. And as it's passing the horizon, it can't leave much of an imprint because, again, the adiabatic principle says that things that appear later, because of the adiabatic principle, the relevant modes are it leaves them in their ground state. Things that appear later don't have any memory of what happened earlier on, and so we seem to get irreversible evolution, where the final state does not know everything about the initial state. So in quantum mechanics, in quantum field theory, even until you get to black holes in string theory, we believe that the basic framework for quantum theory is Schrödinger evolution. But Schrödinger evolution is reversible. You can take it forward in time or backwards. And this thought experiment throwing the book into the black hole is saying that, in fact, black hole evaporation can't be described by Schrödinger-like evolution because you can run it forward, but you can't run it backwards from the final state to the initial state. So, and that's Hawking's original argument. And what I'll do next time is to make that more precise by talking about entanglement entropy, as introduced especially by Don Page, and then Hawking's explicit proposal that Schrödinger evolution is replaced by dollar matrix evolution. And then we'll go on from there. So I guess all of the senior folks can leave, and we can have more questions. Is that the plan?